Okay, good evening and welcome to the week 11 live session for the GPU Architectures and Programming course. Let's get started. We will go through a detailed recap of this topic since some of you may be new to the whole neural network part. And then we will solve a few questions. They may not be directly related to the neural network topics because, as you may have noticed, I think there's a subjective assignment for this week. And there are not a lot of MCQ type questions for week 11's content, but we will solve a few questions that involve concepts from the previous weeks. And please note that next week will be the last live session for this course. So if you have any questions or doubts that you would like me to address, please put it on the discussion forum or send it as an email or whatever works for you before this coming Saturday, right? The next Saturday basically, so that I can address it in the next Sunday's live sessions. So that 14th April basically will be the last live session you will have for this course. With that, let's get started. So in week 11, we looked at a bunch of things in the neural network space. So we started off with what is machine learning, what are the different types of machine learning paradigms. We looked at linear regression, we looked at a multi-layer perceptron, we looked at neural networks, looked at things like the loss function, the gradient descent and the backpropagation. Then we went on to see what a DL library such as PyTorch and TensorFlow needs to offer. This notion of a computation graph, which is what the libraries use to represent neural networks. Finally, we looked at layers in a CNN, what these layers are for and so on. Let's start with a recap. Yeah, so coming to the types of learning, you broadly have three categories of learning, right? So one is supervised learning, the other is unsupervised learning, and the third is reinforcement learning. So reinforcement learning is kind of out of the scope of this course. We won't talk about it a lot. So supervised and unsupervised, I'm sure all of you have learned, right? So basically in supervised, you have some examples that help you learn something. That's why it's called supervised. Whereas unsupervised, clustering is a very good example, right? You're not given something a priori, you instead come up with these clusters. So let's go into the details of some of these paradigms. So with supervised learning, what happens? So maybe I'll zoom in a little bit so that this is visible. So you have training data that goes to a supervised learning algorithm, which basically tries to build a predictive model, right? So this model basically takes the input data and gives you a predicted output, and this is compared with the actual output, because again this is supervised, so you know what the actual output is going to be, and you use some sort of a metric which basically calculates the distance between the predicted output and the ground truth, or what your example tells the output should be. So both are fed into this loss function, and that gives you an error signal. Basically, how far away is your prediction output from the real output, from what it is supposed to be, right? That is fed back into the predictive model. So this model, which is shown as a black box here, is your neural network, right? So this is broadly how supervised learning works. And again, you have this notion of training, testing and validation, which we won't go into right now. So yeah, let's look at this definition that was taught in class. So basically, you can characterize the model that you are trying to learn by some parameter theta, and you define a loss function which calculates this error between the predicted output and the actual output. So one very simple thing you could have is the difference between the two, or you could have square root of things like that, right? So those are your loss functions. Now, based on this loss function, what do you want to do? So this loss function gives you a metric of how far away the predicted and the actual outputs are. So you want to minimize this loss function, meaning that you want your predicted to be very, very close to the actual. You want it to be as close as possible. So in order to do this, you update this parameter theta that you're trying to learn. So the more the loss function is closer to the minima, we'll see what this minima is in a little bit, your predicted output is very close to the actual output. This is called parameter estimation. Now we'll start off with linear regression. So broadly there are two things you can try to do. One is classification, where given an object and given certain classes, you're asked to classify, or you're asked which class does this object belong to, right? So you give an output. Regression is not like that. It's different from classification. Here you are actually trying to predict the value, right? So here, given a data set xi, yi, learn a function f theta of x equal to y that can predict any unknown xj that's not in the data set with a label yj. This function, again, this is linear, so it's like a simple line, right? So you have a slope w and an intercept b. These are the parameters, the thetas that we spoke about previously, that you need to tune. So this basically takes an input x and it predicts y, which is f of x. Now we saw some examples of this, but we'll come back to this. There's also a linear classifier, which is perceptron is the very popular one. Again, here you have a data set. You learn a function f theta of x equal to y with a label yj. Now again here f theta is of a very similar form here, and yeah, the only difference is that's doing regression and this is doing classification. We looked at a few examples here. For instance, there is the NAND function. So we spoke about whether, so we came up with the truth table of this, then we represented this in our coordinate system, and we were trying to reason about whether these points are linearly separable, right? In this case, they are. We also took a second example, I think XOR, where they did not look linearly separable, and in that case, we resolved that situation by expressing it as a combination of two linear functions. So now, what is the building block of a neural network? So you have this neuron basically, right? So your things that are shown in yellow here, x1 and x2, are your inputs, while this gray part is a neuron. So the edges that connect these inputs to the neuron are called the weights, right? They have weights w1 and w2 here. So the value that goes to the neuron is not just the input multiplied by the weights. So to this neuron, what goes is w1 x1 plus w2 x2, which can be written as sigma wi xi. Now what comes out of the neuron? It's a nonlinear function. Remember, we spoke about, we'll talk about some of these nonlinearities and nonlinear functions a little later. But basically what you get is a sigma of f. So this is your input, and you apply some nonlinear function here, and that is your output of the neuron. This is a building block of a neuron. So yeah, like I said, here are some activation functions. So sigmoid is a common one, hyperbolic tangent or tan h is another one. A rectified linear unit or ReLU is also a very common one. So this is how all of these look. Now, so if you have a simple neural network or a multi-layer perceptron, what does that look like, right? So you have two inputs here, x1, x2. You have one hidden layer here, which has 3 neurons. And like I said, all of these will have weights. So here every input is connected to all 3 neurons and they have different weights, right? So that's what goes as inputs to the neurons. Then you have activation functions here, and then that's what comes out of the neuron. And then finally there is the output layer, which has 2 nodes, and this one gives a probability. So the inputs here are hours spent studying, hours spent programming. Based on these 2 inputs, you get 2 outputs from this network: probability that you will pass and probability that you will fail. So this is a classification example. Okay, now let's look at regression. So this again tells you a little bit about how regression is versus how classification is, right? So again here the inputs are the same. You have one hidden layer. Now your output is percentage of marks scored. It is not trying to predict whether you will, it's not trying to say whether you will pass or you will fail. Instead, the output is percentage of marks scored. Okay, so what are neural networks? Each neuron, so neural networks basically have multiple layers and multiple neurons, right? So every neuron accumulates a weighted sum of the inputs from the previous layer. This we already saw. Once it does that, it applies an activation function to its input and propagates the output to a neuron in the next layer. So this results in a series of linear and nonlinear transformations from the input layer to the output layer, because your activation functions can be non-linear, right? That's why it's not all linear transformations. Also, if it's all linear transformations, you wouldn't have a network with many layers, right? Ultimately, you could represent all of them as one single transformation. So because there is this non-linear transformation, you cannot do that. The predicted output value for every input example is a function of the input feature values and the weights and activation in the network. So yeah, here is an example of what actually happens in terms of the weights and the activations. We won't go through this in detail, but basically this is the forward propagation. It's also called the feed forward propagation. So in a neural network, there are two different types of computation. One is the forward propagation, where you are given some inputs, you put them through the neural network and you get the output. The other part of the computation is the back propagation, which we'll also look at briefly. Right? So now this feed forward propagation can be expressed this way, right? So z equal to x into w, x is your input, w is your weight, right? Then you have an activation that basically applies some function on this z. So a equal to f of z. Now again you have a second set of weights here. So the input to this output neuron g is equal to a, which is your output of this neuron, into the second set of weights, which can be called w dash. Again you have some activation function here. So o equal to f of g, right? That's the function that's applied on g. So this is the feed forward propagation, very succinctly expressed as a series of matrix transformations. Okay, now given the structure and the weights, we know how to compute the predicted output value for an input example. Now, some terminology things here. So the structure of the network itself, the number of layers and the number of neurons per layer are called hyperparameters, and the weights are the actual parameters. So theta, basically all your w's. So training involves minimization of a cost or a loss function, which we already spoke about. So what is this loss function? We can take a simple example here. J of w equal to half sigma I 1 to n yi minus oi, again a square, right? So yi and oi are the actual and the predicted output. So here you're taking the difference, squaring it and then summing it. There are different types of loss functions. This is one of them. And again you have the feed forward propagation equations, and you can substitute those into this loss function and get this expression. So that's about the loss function. Now you are trying to minimize this loss function. So you have to find the values of w and w prime so that jw is minimized. So compute del j by del w and del j by del w dash. Instead of setting these to 0, we perform numerical gradient descent, and you update these weights in the direction of the steepest gradient descent. So this is what it looks like visually, right? So you start off at an initial point somewhere here, and you're trying to go to the global minimum of the cost, right? So you keep making changes to your weights along that direction, and you finally arrive at the global minimum. That's your gradient descent. So this whole part is called back propagation. So like I said, the first part is your feed forward propagation, where you obtain predicted output values for each input value. So once you have the predicted output, you can compute the loss function. Then you compute del j by del w for all the weights, update the weights with the gradient, and repeat this till there is no change in gradient. So this is said to be convergence, right? So this is the feed forward and the back propagation. So in summary, you have forward propagation, which is a series of linear and non-linear transformations starting from the input layer. Back propagation again involves linear and non-linear transformations starting from the output layer. So one goes like this, the other like this. Now, each operation and transformation exhibits parallelism and scope for optimizations using a GPU. So, this is what is of interest to us. Again, why are we going into this? Neural networks are a very common example of an application that uses the GPU. It's very relevant in today's tech scenario. So, we are looking at them particularly. So, we try to understand a little bit about what these computations look like. Now we'll go into detail about how these are executed on the GPU, how there is parallelism, and how we can use that parallelism. So let's move forward. So we go into, after this, we go into what a deep learning library should have, right? So deep learning library basically helps you write code for neural networks efficiently without having to implement everything all by yourself. So by default, it should have constructs for specifying the network. So given that the layers in a network are all fairly standard, you don't need to implement each layer on your own. You can simply call, the library would have already implemented the layer for you and provide you with APIs that you can call, and you can use those to specify your network. Again, these operations like forward propagation, back propagation, and gradient computation are implemented by the library and are implemented efficiently so that you don't have to do it. You can simply use the functionality that it provides. And it provides routines for training and testing. Should also support parallel and distributed processing. Basically, you must be able to use maybe multiple CPUs or multiple GPUs if you want. So common deep learning libraries are TensorFlow and PyTorch. There were also a few others like Theano, MXNet, which are no longer so popular, but yeah. So now, all of these deep learning libraries use most of them use an abstraction called a computation graph. So what is this computation graph? It denotes the functional description of the required computation. So a node with no incoming edge is a tensor, matrix, vector, or a scalar value. A node with an incoming edge is a function of the edge's tail node computation. An edge represents a data dependency between nodes. A node knows how to compute its value and the value of its derivative with respect to each incoming edge's tail node. So these are some properties that you need. Can we expect subjective assignment kind of questions for final exam? No, I think I checked with the TAs. This was asked to me initially in the course, I think. So I checked with the formal TAs. So before I answer this, just a disclaimer, I am not involved in setting the final exam questions. The TAs who kind of answer your questions on the discussion forum about all the assignments will be doing that. I think I checked with them, and I remember telling you guys also that there would be only MCQs, no subjective assignment. But just to be doubly sure on this, please ask on the discussion forum once and get an official confirmation. But as of what I know, there are no subjective assignment questions for the final exam. It would be purely MCQs. Hope that answers your question. Great. Yeah, so yeah, these are some properties of the computation graph which you may generally know, right? For instance, if there's an edge between two nodes, it represents the dependency. Additionally, there are some properties that come in because of the deep learning computation itself. For instance, this being able to compute the derivative with respect to the incoming edge's tail node, things like that. So yeah, so let's look at how this looks like. So here again, this representation was what we saw earlier. Now we are looking at the computation graph. So x and w go as inputs to this function z. So we can simply write it as a function that takes in two inputs and gives you the product of the two. So this is your input to this set of neurons. Then you apply an activation function. So this is the next node. and that is sigma of u. So basically whatever comes here as an input, it applies some function onto it, and that's the output of this node. Again, if you have a second set of weights, these two are now multiplied at this output node, which is again fuv equal to uv, and then you have a final activation function. So this is the computation graph representation. So as you see, there are dependencies are represented by edges and things like that. You can go through these previous definitions and this visual representation to clearly understand. So again, what are the computations that are there in the forward and the backward? So forward computation, you loop over each node in topological order and compute the value of the node given its inputs. Backward computation, loop over each node in reverse topological order, compute the derivative of the final goal node with respect to each incoming edge's tail node. Now, what does a convolutional neural network look like? It's very similar to vanilla neural networks. These are primarily used for image classification. So, an end-to-end CNN network expresses a single differentiable score function from the raw image pixels on one end to class scores at the other. So, you might have seen a very simple example that maybe does cat and dog classification, right? So, ultimately, so your input would be an image of a cat or a dog, and then your output would be scores corresponding to each class, which you can think of as a probability that this input belongs to class A, class B. Yeah, and these have neurons arranged in 3 dimensions: width, height, and depth. And we'll also see what are typical layers. So typically you have an input layer, a convolutional layer, pooling layer, ReLU, and fully connected. So fully connected is typically used at the end where your 3D image volume is flattened, and because ultimately at the end you just have a classification type of output, right? That's why this is done. And the other layers, all inputs and outputs, are 3D image volumes. So we look at what each of these are used for. So convolution layer is the core building block of a CNN and is computationally expensive. So input is a 3D image volume, output is also a 3D image volume. The dimensions of the output are dictated by these parameters: the depth, stride, and zero padding. We look at what these are in a little detail, then you'll understand. So here is an example. This is your 2D input image. Let me just get a pen. Yeah. Is this visible? Yeah. So this is a 2D input image I and a 2D weight filter. So this can be called, you'll hear terminologies like filter or mask. All of these are the same. Sometimes you may also hear kernel. All of these are the same. So the convolution operation basically slides this filter over the input image like this. For instance, here, here, and here, right? It's very much like a sliding window operation, and then computes a neighborhood operation, typically a weighted sum. So you'll do something like this multiplied by this plus this multiplied by this. So all of these will become basically one element in your output. So the output size will be determined by various parameters. We'll come to that in a little bit. So this is one example where you have multiple filters. So you do the same operation and then you do an element wise addition over all of these to get one output. Now let's look at what are the parameters and the hyperparameters. So the convolutional layer has a 3D weight matrix, or basically an array of 2D weight filters. So we had seen one filter and how it slides over the image. You could have an array of such filters, and those are the parameters. Basically that the weights of that filter are your parameters. The dimensions of the output are dictated by 4 hyperparameters. These are number of filters, the filter dimension, stride, and zero padding. So again, understand clearly the difference between parameters and hyperparameters. So the parameters are learned during the training process itself. The hyperparameters are things that are kind of experimented prior to the training, and they are fixed. During the training, they don't change at all. They are not learned in that process. Typically, users do a grid search or something like that to figure out what these should be. So now we look at some of these terms, padding and stride, right? What does this mean? So padding means, padding of p equal to 1 means this is your image. Apart from that, you pad it with, when you say 1, you're going to pad it in both dimensions with typically zeros, right? So this is what padding of 1 means. So your kernel or your filter will basically start from this position. Now stride basically tells you the the increment by which this filter moves every time. So let's say it starts here. Now if my stride is 1, it's going to move one step to the right. If my, this is stride equal to 1. If my stride is 2, it would directly move here, right? So this decides what is the step size of by which your filter moves. So that's the difference between stride and padding. Hopefully that's clear. Let's look at the question. For subjective assignment, we have to submit in the form of .txt. Tried Google Colab. Process is not working now. Again, I won't be able to help debug this without seeing what is the error, right? So whatever your assignment says that you have to submit, it would be better if you submit it in the same format, because typically assignments may be graded automatically. There may be an automated process. If you tried the instructions that were provided in week 3 and you're facing a particular error, then it would be good if you can post that error on the discussion forum so that the TAs can help you figure out why that error is happening. Have you already tried that? And did you get an answer as to what you can do? I don't see a question on the discussion forum so far. I'm just looking at the last week's questions. Okay, that would be the best thing to do. I think someone has, because I can't help you figure out the answer. So if you have access to a GPU, then it may be possible to try out locally as well. But if not, then Colab is probably the easiest one. And given that you have a video that tells you how to do that, that would be the best option. So without knowing what your error is, I won't be able to help debug it. But you can ask on the discussion forum. I think someone else also has asked and they've received an answer. So you can ask there, and then that will help you figure out. When is the deadline for this assignment? 10th. Okay. Then it would be good if you can ask today itself after this session, so that even if they take a day to reply, you'll still get your answer before the deadline. But these things, as and when you face issues, please ask, because deadlines are very close, right? So you may not have a lot of time otherwise. Sure. So this is padding and stride, and let's move to, I think we have a little more recap, and then we'll move to the problem solving. So convolution and matrix multiplication. As we saw, convolution essentially performs dot products between the filter weights and patches of the input image. So we also saw in the lectures how this was leveraged to formulate the operation of convolution as a matrix multiplication. And this is typically done as well. Now pooling layer, pooling typically applies a downsampling transformation. So usually you will see max pooling or average pooling, which means that if you have let's say a 3x3 set of inputs where you're trying to do a max pooling, you'll take max of this whole neighborhood. If you're trying to do average pooling, you would take the average of all of these. and this does not have any learnable parameters. As you can see, it's a very simple operation, right? Max or average. So it's purely a transformation operation. Again, inputs and outputs are 3D image volumes. So an end-to-end CNN could look something like this: convolution, pooling, then you have fully connected layers at the end, basically, which gives you outputs for each class, the probability or the score. So with this, we come to problem solving. Let's maybe do a couple of problems and then take a 5-minute break. Again, like I said, problems will involve concepts that you've learned in previous weeks, because I think I didn't find any questions on week 11 content itself. Week 12, I think there are specific questions. So some of these problems may involve things that you've learned previously. But let's try going through them. Okay, let us consider, so this data is common to 1 to 5 and it's a bit long, so go through it a little carefully. Consider a 1D neighborhood operation, say reduce, which is a spatial transformation that takes as input a 1D array of A of size n and produces a 1D output array B. This is obtained by considering a 1D window of size k and sliding it along A in strides of k. So this is a 1D array. Let's just draw this. So the size of this is n. Now you're performing a reduction operation which transforms this A into another 1D array which is called B. How is this transformation done? At a time you take a window of size k and then you slide it along A in strides of k. So the stride and the window size is same, which means that there will be never any overlap between the windows. Each window is going to be a distinct set of k elements, and therefore so whatever you compute over this window, one element is stored in B, right? So total number of elements that is computed, or the size of B, is basically n by k. So size of A is n, you have k such things, and each of these becomes one element. So totally you have n by k. In this case, you assume that n is divisible by k. Now here is a simple example. A is 1, 2, 3, 4, 5, 6, 7, 8. So n is 8. K is 2. The stride and the size of each reduction is 2. Now the output array is therefore size of n by k, which is 8 by 2 or 4, right? And in this case, the reduction operation is an averaging operation. So what do? First you take two elements, 1 and 2, average is 1.5. 3 and 4, 3.5, so on. So that's how you compute B. So first entry of B is average of A0, A1. Now consider the following incomplete code snippet where the reduction operation is computing maximum. So this was the average reduction operation. Now you are given a code snippet that is computing max of elements. So this kernel is launched with a 2D grid of 1D blocks, where each block is responsible for reducing k consecutive elements to one element, same as what we studied. So window of size k is moving in strides of k. So k equal to block dimension dot x. Now let's look at the code snippet. So this is the reduction kernel snippet. A, B, N, TID equal to block idx dot y star grid dimension dot x plus block idx dot x star block dimension dot x plus thread idx dot x. Bound equal to dash, block size equal to dash. For s equal to 1, s less than block size, s star equal to 2. If TID mod 2 star s equal to 0 and TID plus s less than bound, A of TID equal to max of A of TID plus s. And then you have a sync threads. If thread idx equal to 0, so this is basically your reduction operation. B of blank equal to A of blank. Now your first question is choose the correct option to fill in the blank marked as A. So A is this, bound equal to dash, and you have 4 options. So I think this part is clear. All that you need from here is that it's a 2D grid of 1D blocks, and k equal to block dimension dot x. So I'll pause here for a minute and then go to the options. Okay, let's look at the options now. So today I won't discuss all of these in a lot of detail because, like I said, they involve previous week's concepts. So go back and look at the answers and try to solve these on your own. And if you're unable to and you have a doubt on any of them, please post it on the discussion forum and we'll discuss it in detail in the next week. Okay, let's look at the answer. The answer for this is B. 1 plus block idx dot y star grid dimension dot x plus block idx dot x into block dimension dot x. So why is this? So first of all, what is bound used for? So TID of S less TID plus S less than bound. So this is basically used to access A, right? So you want to make an axis that is within A, right? You don't want an out of bounds axis. So ultimately, that's what your bound helps you do, right? So it's the max element or the max index of A that you can access, that is present in A. Anything greater than that will be an out of bounds axis. That does not make sense, and it may lead to errors and illegal accesses, right? So here, if you look closely at this, you'll see that this is the block ID formula, and 1 is used for because it starts from 0, and then you multiply that with the block dimension. Again, this is a 1D thing, so it's just block dimension dot x. So hopefully this is clear. Like I said, I'm not going into too much detail here, but go through this, and if you have doubts, please ask me. So we'll move to the next question. Choose the correct option to fill in the blank marked as B. So let's look at what B is. So B is the block size. I'll again give you maybe a minute to solve this. let's look at the answer. This is fairly easy. Block dimension dot x. So you're already told that it's 1D blocks. So it's simply block dimension dot x. So next we are asked to fill in C. Let's look at what C is. C is this. So basically you're performing this reduction operation on some element of A, and then you're populating some index of B, right? So you're asked to fill in what is this. So take a minute to think about that and then we'll discuss the answer. So block, yeah, we will at C. Okay, let's look at the answer. So it is C. So again, I'll give you a very intuitive idea of how this comes. So again, we know that we are going to take, say, a k window of elements in A, and then we are going to perform a reduction operation, which in this case I think was max, and then populate it here. So now, if I'm looking at, say, uh, this block of k elements, I'll need to, there would be one element each for these two that are already populated in B, and this has to go to the third element. So this basically will tell you why the answer is this. Again, I won't go into details more than that. We've solved a lot of questions in this pattern, so this should be fairly easy by now. So with that, we'll move to the next question. So choose the correct option for the blank marked as D. So D was again very simple. So we looked at what index of B should this element go to. Blank D was what index of A is used. So again, let's look at the options for this. Yeah, here are your options. Okay, let's look at the answer. So the answer for this is D. Block idx dot y star grid dimension dot x plus block idx dot x star block dimension dot x. So I think this goes back to your thread ID calculations, right? Look at that and I think this will make sense. We'll move to the next question. Given the code snippet, with 2D grid of 1D blocks and n equal to 4096, k equal to 64, which of the following is a valid launch parameter for the reduced kernel? So you have four options. Again, very similar to questions we've previously solved. I'll give you a minute. Okay, let's look at the answer. The answer is B. So again, one thing that you can do is multiply all 6 of these and see if it comes to 4096. I'm not going to try that out, but that's something you can try. And you're already told that this is going to be 1D, this is going to be 2D. Unfortunately, all the options are of that pattern, so you can't eliminate any of them. So K would be 64, which gives you an easy answer of this one, right? And then you can use, if there are multiple options having 64, 1, 1, you can use this product method to see which one of these matches. So the answer is B. Let's move to the next question. I think we'll wrap up early today. I have probably 3 more questions. Consider the following kernel snippet: warp size, define warp size, and this is assigned lane, LID equal to thread ID x dot x, GID equal to block ID x dot x star block dimension dot x plus thread ID x dot x, lane equal to LID ampersand warp size, G data of GID equal to lane. The above kernel is launched with the launch parameters 16, 128. After the values of G data are assigned, a standard reduction kernel is called, which calculates sum of all elements in G data. What is the final sum? Here are your options. I'll give you a minute and then we'll discuss. Okay, let's look at the answer. It is A. Let's see how we get there. So the warp size is given as 32 and the launch parameters are given here. So every block of threads contains 4 warps, basically 128 by 32. Now every thread belonging to a warp will have lane values ranging from 0 to 31. So basically what we did to compute lane is LID and warp size. LID is your thread ID, right? So you take the local thread ID and the warp size and perform an AND. So for each warp you would get values from 0 to 31. Now the reduction kernel calculates the sum of all elements. So in every warp you would be having 0 to 31 summed up. This is 496. Again, double check this. Now you have 4 warps. So the sum for each block is 496 into 4, and then you have 16 blocks. So that is 16 into 496 into 4, which comes out to 31744. Again, verify this calculation, but I think this is fairly easy. Let's move on. Consider the two given scenarios and choose which type of fusion is more efficient for a GPU which has 16 SMs and can accommodate 2048 threads at max per SM. Also calculate the total number of cycles it takes for the fused kernel to execute on the given architecture. So you have K1, K2 and K3 and the dependencies are like this. Launch parameters, K1 takes 30 cycles, K2 takes 40, K3 takes 70. K1 is 82048, K2 is the same, K3 is 162048. So you have four options: inner thread fusion 140, inner thread 100, inter block 110, inter block 100. So which is the um, um, efficient type for this particular GPU is your question. I'll give you a minute. Let's look at the answer. The answer is C, interblock fusion 110 cycles. So by the dependency graph, you can see that K1 and K2 can execute concurrently, and only after both of them finish, K3 will execute. So interblock fusion will give you a cycle count of max of these two, 30 plus 40, and then K3 will take the same 70 cycles. So max of 30 and 40 is basically 40 and plus 70, which is 110 cycles. So this is the answer. Think about why this is the most efficient, whether others are possible, etc. If you have questions, let me know. We look at the last question for today. So here is another scenario, K4 and K5. Launch parameters are 16 and 1024 for both. Both take 40 cycles. Again, the question is the same. Which one is more efficient and what cycles does it take? Inner thread 80, inner block 80, inter block 80, A and B, all of them. Okay, let's take a look at the answer. So the answer is options A and B, which is basically inner thread 80, inner block 80. Why is that? So basically there's a dependency, as this edge indicates, between K4 and K5, meaning K4 has to execute, only after that you can execute K5. So regardless of whether you do inner thread and or inner block, it will still take you 40 plus 40, 80 cycles, as the target hardware does not need batching for these two type of fused kernels. And for inter-block fusion, you cannot synchronize across blocks, so that's not even feasible for this scenario. So A and B, which is inner thread and inner block, are feasible, and both of them take 80 cycles because of the dependency. So with this, we come to the end of this session. Like I said, none of these questions are very relevant for week 11 itself, but I thought it would be a good idea to have a sort of a recap sort of thing from various other sessions. So I've not gone into detail of any of this, but in case you need explanations, please let me know ahead of time. And like I said, it's next week is the last session. So any doubts that you have, please ask them beforehand so that we can address it in next week's session. I'll stay around for a minute more and then we can end this week's session. Thank you so much and see you next week.